Greetings and salutations to you, my fair weather friends. Here we go, lesson 752. We're going to be covering examples 4, 5, and 6 in the second half of our lesson on parametric equations. Are you ready? Are you? Are you ready? Well, you're watching this, so you better be. So let's start up here at the top with example 4. It says that sometimes we're going to use the angle as a parameter instead of time. All right, so that's how it can work. And the cool thing about this, and I don't know if they tell you this in the book, but I'm going to tell you, is that this allows you to draw conic sections in parametric form. I mean, we've already done parabolas, but we can draw other conic sections in parametric form, or we can convert from parametric to the regular old function. We can put it in the form that we're used to from a few lessons back. We can see an ellipse, for instance, like we'll have below. We can see it in both parametric and we can see it in our regular format where we graph the thing using the conic app. So let's look at this one here, for example, that this here is one of those with an xt and a yt and 3 cosine theta and 5 sine theta. Now, if you want to go ahead and pause, go ahead and do that and type this in. You're going to try to type in the theta, but you can't. You're going to push the button and t is going to come up, and that's fine. Just let it be as you type it in 3 cosine theta and 5 sine theta. So it should look like this. Okay, 3 cosine t and 5 sine t. And when you hit graph, I want you to watch this happen, okay? Watch it happen as it graphs this parametrically. Oh, it goes in a circle. And did you know which direction does it go? It goes around in an anti-clockwise direction. When we trace this out, we can see this here at time 0 is 3, 0. And as we go around the circle, we get to the top, and it's at, surprise, 0, 5. And then over here is negative 3, 0. And at the bottom, it's 0, negative 5. You see that? 0, negative 5. Okay, so that's an ellipse. And it's, as we can see here in the equation, 5 in the y direction and 3 in the x direction from the center. Pretty self-explanatory, yeah? How that one works. See, our job here is not to keep it that way. Our job here is to put this in rectangular form, put it back in the function mode. So here's the method. We take this x equals 3 cosine theta and we solve it for cosine theta. Okay, we divide both sides by 3. We do the same thing here with y equals 5 sine theta. We divide both sides by 5. Now, look at this. Here comes a little trick and we'll pull out of our bag from chapter 5. If we use the Pythagorean identity, which says that cosine squared theta plus sine squared theta equals 1, and we substitute in for cosine theta x over 3, we substitute in for sine theta y over 5. Oh, you can already see it coming, can't you? Because if I rewrite this thing like this, what does it look like? It looks like one of those. And I know that you have seen this before because that is the form of an ellipse. Yes, indeed it is. And let me show you what that would be like on the calculator here. I'll do that in just a few seconds. If you want to hit pause and try it yourself before I get there, that's awesome. Here I've gone over to our conic section app. I pulled up ellipse. And we're looking at form number 2. Remember, see it's taller than it is wide. It was 5 in the y direction, only 3 in the x direction. So I'm going to pick number 2. And there's our numbers. This is the setup. X minus nothing and y minus nothing. So h and k are 0. Okay, oh, there goes the laundry. A is 5, B is 3. And when we graph it, yeah, that is the same thing. When I trace this, look, 0, 3. Get to the top of the circle, 0, 5. 5, I guess it was 3, 0, 0, 5. Negative 3, 0. And at the bottom of the circle, 0, 5. So you can see that it is the exact same thing just in a different form, but we don't get to see it. Well, I guess this program draws it in the way that it would have parametrically, but sometimes it'll just pop up and there it is. It's an ellipse. Same graphs. Second one graphs it more or less all at once. The first one, it shows us how it would draw it in that, I say anti-clockwise direction. It shows it by increasing the angle. What is it at 0? What is it at 90? What is it at 180, 270, and around the circle to 360? Now this might be a good point to pause and go ahead and try the guided practice number 4 there at the bottom of 466. Should be pretty easy if you do it exactly the same way as this was. And then you want to graph on the graph paper provided what that's going to look like in the function mode. So go ahead, do that. What are you waiting for? Yeah, so hopefully you just graphed another ellipse. That's the deal. Oh, we'll check that out when you bring it to class. Now, moving on to example 5. They tell us in the book that from example 1, they actually showed the same exact parabola, but it had 2 or 3 different instructions to do it. Some of them it happened faster, and some of it happened slower. You see over here on my notes, I'm going to do 5A, 5B, and 5C from the example 5. And I want you to write down in your notes speed, slow, medium, fast, slow, medium, fast. How do you see it? It's going to draw the thing out, and you're going to tell me, like, how fast does it draw this thing out? Does it take forever, or what? You notice that there's just going to be different parameters here. Here t equals x, here t equals x equal 4x plus 1, and here t equals 1 minus x over 4. So watch the speed, but then also watch the direction that the parabola gets drawn in. Okay, that's what I want you to write down: speed and direction. And maybe you could draw it out yourself, and you put the little arrows to show what's going on there. So what are they going to do with these? On all 3 of them, you've got the same equation here in regular form. Y equals x squared minus 4. It's a parabola. Y equals x squared minus 4. Y equals x squared minus 4. They're just changing the parameters here. First parameter, we already said this, t equals x. So if we want to put this in terms of parametric, we substitute into the second equation x, we put in t. Y equals t squared minus 4. Let's look at how fast that goes, okay? Put in t, and we hit graph, and see the direction that happened? Do that again. I have to, like, push the button here and make it. Here we go. And as we trace it, we're like, oh, that moves along. Here it comes from left to right. Off it goes into the distance. Okay, now let's look at the second one. Here's our equations: 4x minus 1 for t. If we replace in our thing, we solve for x. Solve for x by subtracting 1 from each side and then dividing by 4. So x equals t minus 1 divided by 4. And then we substitute that in for x in the second equation, t minus 1 over 4. And you don't have to do the expansion on that. You can just leave it in that form. That's what I'm going to do. So I'm going to go ahead and hit pause for myself and flip it over to that graph. I'm going to graph it, and you watch how fast this happens. Boop. And then by magic, there it is. I've already typed it in. Already typed this sucker in, and let's see what this looks like when I hit graph. Oh. Well, there it is. Okay, so I gotta type in a letter here, and then let's see it. Oh, it took a little bit longer. And I had to fiddle with the window here too. I had to make the time go bigger, because when I had it on the same window as the other one, it just gave me a little itty bitty piece of the thing. I want to see the whole thing, so there we go. When I hit trace, look, it takes it forever to come around. 6, -6, -3, negative. There's 0 seconds, and then oh, it struggles to make its way around there. And which way did it go? It went from left to right, just like the first one did. Third one, down here. You see, I said I had to change my time things to see the whole parabola, but you're smarty pants, so you can do that. You can figure that out. So here's the last one where time is equal to 1 minus x over 4. we solve this in terms of x, so that involves moving some pieces around. The math turns out to be this: x equals 4 times 1 minus t, or if you expand that, 4 minus 4t. Plug that into the other equation. I'm just going to leave it like that instead of doing the FOIL method, because this will work just fine. Boom, there it is again. 4 minus 4t, 4 minus 4t squared minus 4, and watch this, people. Oh, well, that's exciting, isn't it? Okay, let's type in something so it thinks I did something different, and boom, laser blast. Okay, what was different about that one? Obviously it was fast. I actually slowed it down a little bit. Let me show you how fast it was the first time I did this. Change this to 0.1. It was like what it was for the other ones. Watch this. Oh, well, that wasn't terribly exciting. Do you see which direction it went this time? From right to left, okay? But it's the same exact shape, the same exact parabola, but different parameter, and so it goes at a different speed. So that was all jolly good fun, and if you want to, you can go ahead and try the guided practice 5A, B, and C. You're going to take the equation x equals 6 minus y squared, and the first thing you're going to do is you're going to solve that for y. Then you're going to do the same drill that they did with the example, and you're going to replace, you're going to solve those things in terms of x, and then plug them into a parametric equation with a t in there and see what happens. So this should be the same graph, but they'll go at different speeds and maybe in different directions, different speed and orientation. Now the third thing here, see, this is all good fun because our physics students will recognize this projectile motion. We spend the whole chapter talking about this, and they're going to bring up one special case that's used in physics. I remember the original picture. We wanted to know how high a projectile was going, how far it would go, and then how long it would be in the air, and I showed you the trebuchet game and how that worked. Here I got a little cannon. We want to know if we fire it off at such and such an angle, where it's going to be at a particular time, or maybe how long it's going to take for it to explode on the ground. So the special formula is, and you may want to use that pause button, we're using angle, theta for the angle that the projectile is launched at, t for time, v sub o is the velocity at time equals 0, or the initial velocity, h sub 0 as the height at time 0, and g for gravity. And this happens for problems like this. Somebody drives off the cliff. Somebody fires a cannon. Boom. Somebody kicks a football. 5 seconds. All these follow the same basic thing. So because it's so prevalent in maths and in physics, then we use this a lot. We can do it parametrically, or we can do it regular way. So here's the horizontal equation. In the x direction, we take our parameter times the initial velocity times the cosine of the angle that the thing was launched at. That takes care of the horizontal component. Vertically, here's the magic formula. Negative 1/2 g delta t squared plus t times the initial velocity times the sine of the angle added to the height. Now that's a whole bunch of stuff, but it's basically a quadratic equation. X squared plus something x plus a constant. And it's given that our book is going to use the number 9.8, but in physics we use 9.806 meters per second as the acceleration due to gravity. Or if you're going to be a lame-o and do it in English, do it in non-metric terms, it's 32 feet per second is the number that goes in for g. So what I want you to do is I want you to open your book. I want you to look at number 47, or sorry, number 49. I love the number 47, so I can help myself. But number 47. Go ahead and read that thing about the frog. Read, blah, 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 blah. Okay. If you're not done, hit pause and finish up. Okay, here we go. So I collected the initial information. Here's our velocity at time 0.75 meters per second. There's the angle. There's the height above the pond. that the frog is jumping from, and we are given this in metric. Yes, the metric system. So, if we plug the numbers into our magic formula, 0.3 goes with V sub O, and T cosine of 45. Now, of course, make sure that you are in degree mode. For YT, we've got negative 1/2 times 9.8 gives me negative 4.9. T squared plus, is that velocity there? I put it in front, 0.3 T sine of 45 plus the original height. We got all that stuff in there. And lo and behold, drat. Did you see my mistake? I had putting 0.3s in there. It's 0.75 for that velocity. So 0.75 T cosine 45, and you want negative 4.9 T squared plus 0.75 T sine 45 plus 0.3. First question says, well, after we wrote that, but B says he's going to jump, okay, and it's 0.5 meters away that he's trying to land on the bank, and is he going to make it? Okay, so I set my window to this. Not going to be in there for more than 2 seconds, crying out loud. And we want to make, if he gets all the way to this other side of my screen, then we'll be able to see it, because I set it for 1/2 meter. I set my Y scale for 0 to 2, and a scale of 0.25. So, is he going to make it? Is he going to make it? Let's see. Scrap it. 1/10. Didn't even make it 2/10. Didn't even make it 2/10 of the way there. If he definitely missed. He went kerplop, right? Right off the lily pad. Kerplunk. We trace it out and we see, well, he's in the air, he's in the air, he's in the splat. Oh, he missed by quite a bit, didn't he? Stupid frog. Now the third part of that problem is bonus. Will he make it? No, he will not. I'll fix this at some point, but yeah, bonus question. If the frog was able to jump on a lily pad resting on the surface of the creek 0.4 meters away and stayed in the air for 0.38 seconds, what was the initial speed of the frog? There's the question of the day. Hope you enjoyed this edition of the Flipped Classroom. Goodbye.